afternoon, everyone. Celso Battaglia, Astro 10, and we are getting close to our last days of class, by the way. So we have this week, next week, and then final week. Before I start, I would like to remind you all that the final exam, I sent an email to all of you. Final exam is Thursday at 10 o'clock, 10 a.m. And the room is LE 232, and you must bring a valid identification. I also don't want you to stress, and in case you can't be there at this time because you have other commitments, I'm sort of a flexible. But for that, you need to email me so I could meet you when I'm giving other final exams. So let me just let you know we have a final exam. I could meet you for a final exam on Tuesday. No, let's start with Monday. With Monday from 10 to 12, right? 10 to 12. I could meet you in one of my physics lab. That could be an option. On Tuesday, it's more complicated because I have a class and lecture. So my lab is too noisy and I can't have you there. It's not a kind of a quiet environment for you to complete your exam. Wednesday, it's a possibility. I can see you between 11:30 and 2 o'clock, and I will be in a tutoring center. That's a possibility right there. And then we have Thursday. So other than those days, I'm not possible. I mean, it's not possible for me to come here later or so. Okay, so let me know in case you can't be for final exam Thursday, 10 o'clock, then we should do something else. Now, here's the seed of this week's discussion, and it's going to be the last one. I'm closing up discussions and Astro News, so this is the last one. It's based on, this week is about galaxy, and you have an article to read, which is about a planetary object, I think. Let's see. I think that's what it is. Place this for a while. So we are in March, May 8th. Oh, so there is no, yeah, so that's even better. So here is what I wanted to do. Oh, by the way, you are not seeing my screen, right? Sorry about that. So let me bring my screen here. And this is the article I would like you to read. Since this week is about Milky Way galaxy, one of the important topics of this week is to review or to introduce to the fact that galaxies of significant size, like our Milky Way galaxy or Andromeda galaxy, in fact, all spiral galaxies and all not the dwarfs, but the large elliptical galaxies, they all come with a supermassive black hole in their core. How this black hole tends to be formed is because just imagine again, when we study star formation, gravity would bring gas to the center of mass of that system, and therefore that region is the one that has higher density level than all the others. So same idea is prevailing when galaxies form. So you have gravity force that bring everyone together to the center of mass of the galaxy. So the density of gas there is much larger than in any other part of the galaxy, which means if you are going to find the first generation of star forming ever, it's going to be in the core of a galaxy. So in the very core of the galaxies, stars come in, stars explode, and then black holes are formed in an environment that is highly densely populated by gas. And so this black hole just keep eating up gas and gas and gas, and then eventually they are supermassive. So that's the idea. So you are expected to find in large-sized galaxies black holes in the very core. So this article is about to access gamma rays that happen to be detected in the core of galaxies. And certainly black holes have something to do with it. And up to very recently, the dominant idea was that, well, since gravity is also one of the characteristics of dark matter, so then it could be that dark matter and the WIMPs, weakly interactive massive particles, let me see if I have it here, weakly interactive massive particles, right there, weakly, WIMPs. So these WIMPs, they annihilate themselves if they collide, creating these gamma rays. And that was one of the theories that haven't been proven yet with backup data. And now this article is suggesting something different, that in fact these gamma rays are the results of pulsars that exist in that region. So the question that I would like to ask you is exactly why? Why there is a different group of scientists or astronomers that suggest not dark matter, but something else as being responsible for providing gamma rays emission or excess of gamma ray emissions coming out of the galactic's center. So why is that? Why is not dark matter? Why is gamma ray? Why is something else, which is pretty much pulsars? So give me your explanation. So you have to read the articles, you have to back up your argument, and then we go from there. Okay. Oops, that's not it. No, that's not it either. Okay. Milky Way galaxy. If you have gone to a very dark site and without light pollution, without what we have in our developed city, bunch of illumination, pollution, pollen, but primarily light pollution. We have an observatory, Montgomery Hill Observatory, and quite often we are there with students, and then somebody comes up with a car and big, headlights and say, "Hey, I'm here, so get away from my path." And that's a complicated issue. Amateurs, probably not so much. Professional astronomers, they are photophobic. They don't like to see light because it blinds and then prevents you from seeing and spying on very faint objects. So, but if you are in a dark site and you look up to the sky, you see this patch. See this patch over here? Kind of a bright and dark in the middle. You might be able to see that across the sky. In fact, in our Montgomery Hill Observatory, on dark nights, which means nights the moon is not there, and nights that we could call photometric by the reason of not having a lot of vapor in the atmosphere, not having a lot of pollution in there, clouds are not there reflecting city lights. So if you have a photometric light, so the sky is really clear, you might be able, and I already saw at 11 o'clock when most of the lights kind of settle down, probably not so much street lights, but by 11 o'clock you look up and you can see quite well, and I saw several times, the Milky Way stretching out from Cassiopeia all the way down to the southern sky, southwest sky. And and then you say, well, what is the Milky Way? Is the Milky Way something out there? No, the reason is we are in the Milky Way. Let me see if I can show you this. So, see this figure over here, this picture, like this? Imagine this thing is this thing over here. And we happen to be right here. See that? So our solar system is in one spur, in one little outlet or bifurcation of Orion arms, one of the arms of our spiral galaxy. There are four major ones, and out of these four major ones, you have several spur, and we happen to be in one of it where the sun is, and so planet Earth. Now, if being this spur, and if you look straight towards the center of the galaxy, in other words, if you look straight towards the region of Sagittarius, right? If you look towards the region where the constellation of Sagittarius is, then you might be able to have an impression of what represents to call this as the Milky Way. So we are in the Milky Way, but when you look across imagine the Milky Way is a pancake, and blueberry pancake, and the sun is one of the blueberries in there. So we are inside a pancake looking towards the center of that pancake, and that's what we would see it. We would see basically some stars outside. See the stars over here, these dots? They are also stars in our Milky Way galaxy, but they are closer than those producing this fuzziness out there, up here. See that? And these stars are called in a different coordinate system. We didn't advance a lot in coordinate system, but those stars are called high galactic latitude type of stars, because they are closer and they are not seen along the edge of the galaxy, like in here, right? So if you look towards the edge of the galaxy, along the edge of the galaxy, then we see the picture in the first slide. And let me introduce you to our galaxy. So our galaxy has pretty much 100,000 light years in diameters, edge to edge, if you count. And from where we are to the galactic center, we are talking about 26 to 30,000 light years in distance. So if you could travel with the speed of light from where we are to the galactic center, you would take 30,000 years. So just to give an idea of the dimension. And what is the thickness of the galaxy itself? So what is the thickness of this pancake? I'm getting hungry now. But the thickness is about 2,000 light years of thickness. Okay. And but we didn't know that in the very beginning of the 20th century, which pretty much 1900, and let alone in the 1800, we had no idea. So Herschel, what he did, Herschel, and he had the assistance of his sister that did fabulous work. In fact, the participation of women in astronomy in the very beginning of astronomy was phenomenal, especially if you take into consideration the fact they were not hired the same way as a man was. They were not allowed to get their degrees and work on their degrees. I mean, women would take degrees just to be more educated and be a better household, but not to work and compete in the workplace. And so now we have this so-called heron of what is his name? Pickett. I forgot his name, and they developed the spectral classification using a large amount of women, all dedicated, and so their participation was impressive. So Herschel, what he did some statistics, and his statistic was, here's the sun, and then he looked in the sky all over in all different directions, and then he count what what is the distribution of stars he could see. So if you look at his diagram here, his diagram suggests that the distribution of the stars around the sun are somewhat uniform, right? Which means you take a scoop of stars in all directions, it's basically the same. And his conclusion was, well, since no matter which direction I look, I count the same distribution of stars. I don't see so much in some directions because of dust or because of this dust, which we already know exists in the galactic plane, and that dust is the result of cold gases, indicates star formation and all of that. So Herschel said, well, since the distribution of stars around us seems to be the same, it leads me to conclude that we are in the center of the Milky Way galaxy, right? Because no matter which direction you look, all looks the same. Like if you are in a forest and then you look around and you see the same distribution of trees all around you, then you conclude that, well, I'm in the middle of the forest, and I can't see the edge. I can't see, nothing. And that was his conclusion. Now, another researcher, Sharpley, and he used to work with the globular clusters. And in fact, Sharpley, he was one that had a particular interest in a group of stars in globular clusters called RR Lyra. And RR Lyra are stars that pulsate with a period of less than 1 day. And the interesting properties of RR Lyras are that, or is that, their pulsating period correlates with the amount of energy they have. So, which means the amount of energy they have, the star has, is called luminosity. And we saw that in previous chapters when we studied properties of stars. So if you happen to know the luminosity of stars, then we can use the inverse square law. Brightness is equal luminosity divided by 4 pi d squared, the distance, right? So if you know the luminosity and if you observe the star brightness, and you can use a telescope for that purpose, you can determine distance. So what Sharpley did in his research of RR Lyra in globular cluster was to determine the distance from the sun to these globular clusters. And here's what he found. See this black thing over here? This black thing is Herschel findings, right? Pretty much eye inspecting the star, his eye inspecting the star and doing statistics of the number of stars that he could see it. And here is Herschel's finding and the distance to the globular cluster. So Sharpley, what he found was this. Well, these globular clusters, if we are in the center of the galaxy, how come these globular clusters, which are a group of hundreds or in fact thousands of stars, sometimes hundreds of thousands of stars, how come these globular clusters seems to be concentrated away from the galactic center, if we are the galactic center? So if we, the sun, were in fact the galactic center, he Sharpley would expect all these globular clusters to be surrounding the sun, and they were not. In fact, they were surrounding a region somewhere here, right? Right above the letter B, parentheses, somewhere in there. And then he said, okay, the center of the galaxy is not where we are, but is where I suspect it is, as a result of these different globular clusters encircling that region. And he made um, that proposition, and he ended up being right. And then he became, Shapley, Harlow Shapley. So later on, in fact, Shapley had himself involved in another debate, and that was the debate about um, nebulae. So Shapley believed that all the nebulosity found in our galaxy were in fact part of our galaxy, and whereas Curtis and other astronomers had a different proposition that some of these nebulae, in fact, were extragalactic objects like our Milky Way, but very far away. And of course, Shapley was wrong, which leads to us to emphasize the idea that all statements made in science are not final statements. They are based on intuition and in data available. And if the data available allows you to extrapolate and create suggestions or hypotheses, so you can do that, but the hypothesis must be verified. Up to the point they are verified, it's a fair game. Like the articles that I wanted you to read this week and discuss about it is one final example of that. So we know our Milky Way galaxy has a black hole in the very core. And we know there is an excess of gamma rays coming out of that region. So how to explain that? How to explain the data? So there are two hypotheses or two theories for that. One is, dark matter. So the WIMPs, the weakly interactive massive particles, they are so crunched in there, they might annihilate themselves with collision. And when they do so, they create this spur of gamma rays, right? So that's one theory. And the other theory is one that indicates, it also has neutron stars. And neutron stars, pulsars, in fact, they create and generate gamma rays. And what we are seeing is, in fact, gamma rays. And the point of today's or this week discussion is what sort of evidence this other group, the pulsar group, has that allows them to say, hey, no, pulsars are better explanation. But without data, without building an instrument that can verify what exactly that gamma rays source is, without that instrument, everything is a fair game. And then you can create your hypothesis, but you have to go back and verify and put your hand in the fire, if you will, to and see which idea will continue. One of them will be put it to sleep. So our Milky Way galaxy is an SC, depending on which article you read, could be an SC, I already saw it classified as an SB, but the main point is our Milky Way galaxy is suggested to have a bar. So it's a bar-like galaxy, it's an SB galaxy, but it's very hard and difficult to see stellar distribution in the very galactic center. And so we don't know, but it's suspected that our galaxy is an SB galaxy with different star populations. So if you look at our galaxy in the spiral arms right here, in the spiral arms, the galaxies in the spiral arms, the regions in the spiral arms are rich of star population 1. So star population 1 are young stars. The sun is supposed to be population 1. It's an old star, kind of an old young star, but it's a population 1. Population 1 stars are stars that are in the process of formation or is still in their youth, like the sun is, and they are metal rich as the result of the fact they are formed out of a gas that has been reprocessed over several generations of stars. Now, if you go to the bulge of the galaxy, the central bulge, this bright area over here, the bulge of the galaxy is comprised of star population 2. So star population 2 are um, relatively old stars. They are evolved. Um, if you think about low mass stars, they are already inflating towards the giant phase, and 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 they are pretty much dying out. Population 2, and there is another region in our galaxy called the halo. So the halo is a kind of a spherical region that encompasses the entire galaxy, that goes from 100 to 300 or 200,000 light years um, in diameter, if you think that shell. And the halo has also population 2 stars, so old stars, evolved stars, and it also is a region populated by dark matter. Dark matter. And again, astronomers don't know exactly what dark matter is. There are candidates like the WIMPs, and we know dark matter is there because it provides gravitational tug on all other stars. And I will show this later. Right? So those are the main regions in a galaxy. And if you look not to the bulge, but to the center part of the bulge, it's a region that is inhabited by this supermassive black hole and lots of gas and some excess in gamma rays. And that is it. Bulge, galactic center, the bulge in blue. This pinkish region is the galactic disk. The sun is about 30,000 light years from the galactic center and the halo. And these dots represent a globular cluster. And globular clusters are clusters of stars, population 2, stars evolved. And some evolved stars seem to navigate in the halo as well. Yeah, that's the Orion spur where we are. So how do spiral arms ended up being formed? I mean, which mechanism formed them? So there are interesting ideas. Let me show you something here that might illustrate this nicely. Let's see if this is, I don't know what, Monster Carnival, see if this is decent. Sometimes we get such a junk thing. Spacecom is a good one. Okay, let's see. Since this is Andromeda and Milky Way, let's see if we can get something here going. So in few billion years from now, the two galaxies will collide. Why am I showing this? Because interaction among galaxies exists, and what I want to show you is if the simulation of the spiral arms happen to be shown here. So we have two galaxies, and as they approach, notes that no, this is funny. The spiral arms tend to be developed as they get closer as a result of gravitational interaction. They seem to be very well defined. So pretty much the way this interaction takes place, it goes by the call of gravity forces, basically. Let's see another one. Here's the time. This is too funny. I don't like that. This is too funny. Yeah, I don't know the source of this. I don't want to show that. Sorry about that. Yeah, that's the same. So these simulations are done with antibody simulation. They have several dots that represent stars and mass, gas mass of certain characteristics, and then just let gravity force to prevail, and then you see what happened. Basically, in all these animations, you also have to include the existence of dark matter on it. But the spiral arms there are two possible sources of formation. One is, as you saw in the animation, the galaxy itself is already rotating, right? So you have a rotation going on since the moment the galaxy itself formed. When and this is the result of initial rotation that the gas itself was subjected to. Our solar system was formed initially with a rotation that was later crystallized in these spiral arms, or the spiral, not spiral, but this circumstellar disk. And out of that, everything else we know in our solar system, except the sun, came to be formed. Now, so rotation is in there. So imagine you have a gas that encircles the center of the galaxy, and if star formation start happening in the disk itself, and based on the fact the rotation of the gas is not uniform, which means gas closer to the center will spiral and rotate faster than gas that is further out. And as a result of this star formation, more stars happen to be formed as a result of exploding supernovae. And so we form one star explodes, and then more stars are formed, the more stars explodes, and then you have a propagation of star formation that will light up the gas in that region. But the galaxy is rotating, which means stars that are lighting up the gas that are closer to the center will circle around the center faster than stars that are further out. And then you see this smearing going on. Okay, so this is one of the possibilities of spiral arms being formed. You just have star formation, just add rotation, and that is done. The other theory that explains the formation of spiral arms and being so consistent is the propagation of density waves in the galaxy. So what does that mean? Well, you have a galaxy is not isolated. It is in connection and interacting with other galaxies. And so there is a potential gravity energy that is transferred from one galaxy to another, and that is spread out from the galactic center. So these density waves compress the gas in specific regions, and as a result of this compressing gas, stars are formed, and then you have the spiral arms being formed. Now, this figure is very important. So what is being shown here is this. So if you go from the galactic center all the way to about 17 kiloparsec, kilo is 1,000 parsecs, is 3.26 light years. So from the galactic center up to about 40 or so thousand light years, then the orbital velocity of stars should fall down according to Kepler's law. So stars that are further out of the galactic center than we are should stars encircling the galactic center at speeds that are less than we observe. If you see, for instance, Jupiter or Saturn, as they go around the Sun, they go with a speed that is less than the speed of Mercury and Venus and Mars. Kepler's law, basically, and that's what the blue light represents. It represents the expected rotational speed of these stars. But what you observe is something different. They keep on rotating faster and faster, right? And how to explain that? The only explanation to this, so if you come up with a model and say, okay, let me explain what I observe, it can only be explained here. If you go to, where is that? See this halo over here? If you populate this halo with some material, and it's a material that cannot absorb light, cannot emit light because we don't see and we don't detect, and does not block light from stars in the background. So if you fill this bubble, right, with a material that has these characteristics, does not emit light, does not absorb light, that's why it's dark, and has the property of attracting, so gravity is important, then we can say is this material will pull the stars away to the point that you can verify this curve. So this material was proposed for the first time in the 30s by Zwicky. Zwicky was an astronomer and a physicist and a crazy guy. No one gave him too much attention, but he seems to be right. Zwicky observed, in fact, heavy clusters of galaxies, and based on the orbital and the spatial motion of these galaxies, he would expect these galaxies just to fly away, right? Because they are going too fast. If the galaxies are moving too fast, something is holding them in place. So since he couldn't observe anything holding them in place, he suggested there was some dark material that had the ability of keeping them there in place, like holding them with gravity attraction. But this was in the 30s. Now, when technology was able to provide this data, the one you are seeing now, then a different ballgame came in, and now dark matter becomes some important contributor to the stuff that makes up the universe, about 85%. So if you think the material that make up stars and galaxies that we see, putting there black holes, stars, nebulae, dust and gas, all of that make up galaxies or superclusters of galaxies in the universe, this is pretty much 15% of the material there is. Now, the other 85% of material that has the ability of attracting and producing gravity forces, this 85% is not seen. And then we call that dark matter. Probably in 2-3 years, there will be a viable candidate for dark matter. So far, there are names, but it hasn't been found yet. So these WIMPs haven't been found yet. So, and now the case is pretty much in favor of this existence of dark matter. And this slide shows what lies in the galactic center, not in the bulge, but in the galactic center. In the galactic center, you have this supermassive black hole, and around this black hole, a lot of gas that falls in it and produces X-rays emission, produces radio emissions, and also it was found stars, very massive stars. Andrea Ghez is a leading researcher doing this type of projects. And then there are several of these stars just going about the galactic center. So astronomers use the path of these stars and the speed in which they go and their orbital velocity to determine the mass of the central black hole. And this is the researcher André gives, and and uh, and uh, and that is what is in there. It's a massive black hole, not only in our galaxy, but in galaxies in general. So those are the main topics in our today this week's slide. Start getting ready for final exam, and don't forget to pull up your discussion. All right. Okay. Some students asked me about extra credits. The extra credits are there. I haven't added them yet to the final grade, and I will do as soon as I can get them. Okay. Or if I find a nice way to full Canvas and include that, probably I figure out a way. Let's see. Okay. Bye.